In this video, we're going to look at the last of our conic sections, hyperbolas. This is the last video of the new material. We don't want to forget that we also learned circles in the previous class, so that is another conic section that we haven't really discussed in this video sequence. There will be one more video in this sequence describing and really pointing out how the conic sections vary and how to tell them apart, so please do make sure you watch that as well. This is not the end of conic sections per se, this is just the last figure we have. So hyperbolas, start with the definition. A hyperbola is a set of points in the plane, the difference of whose distances from two fixed points, the foci, is constant. So once again, we have these fixed points, the foci, that are dictating what the shape of the curve will look like. And so hyperbola, as I discussed in an earlier video, almost this parabolic looking shape. Difference being, it's not parabolic. These aren't parabolic because they are approaching asymptotes. And so if we look at our definition, what we're saying is the distance from any point, if we're to find the distance between these two red lines, that would be the same as any other distance. So for instance, if I were to look at, say, this point right here, now the longer line is on the right, but if we were to subtract these two lines, if we were to take this little green piece away from this green section, that distance would be the same as if I'd taken this away from this. So just like with our parabolas, just like with our ellipses, they can be oriented up and down, and not drawn on an axis yet, but we could have it up and down in addition to just left and right, and so this one would be much steeper than the one to the right, and it would have a different orientation, right? So the key is these asymptotes are controlling the ends, and that's why these conic sections are all unique. We can't say that a parabola is just half of an ellipse, and we can't say that a parabola is just half of a hyperbola. They're all unique. There's always a different equation behind them, and so we can't try to model one with the other. Now, let's look at the equations. These equations are going to look very, very similar to those of an ellipse, and so like I said, there is a video for differentiating the different conic sections. But if we start to talk about that, parabolas we saw only had the one squared term. Circles, ellipses, and now hyperbolas all have two squareds. They have the x squareds and the y squareds. Circles, the coefficients on the x squared, y squared were the same. Ellipses, hyperbolas, they are different. And then finally, the hyperbola is the big difference we see here. Rather than a plus, we have a minus between. But beyond that, we see a lot of similarities. To the ellipse especially, it's equal to that 1. Our orientation is going to be dictated by the positive piece. So if the x is the positive, it's going to open along the x-axis, left and right, versus if the y is positive, it's going to open up and down. If we think about our vertex, the same way we've solved the center, the same way we've solved the center every point up till now has always been h comma k. That is still true. The A and the B kind of give us his other sides like it did with the ellipse. If I think about this as being the center, the vertex, we would need to move A units left and right here. Here, also A, up and down. So the A is getting us to the vertices. And so here we're moving along the x-axis, so H plus minus A, comma K. And then here we're moving along the y. So I'm doing this a little bit faster because we did the same operations with the ellipse, just the picture's a little bit different. Now here's where it gets a little different, right? That B is very much different because there's no other side like there was with the ellipse. That B somehow references how to get to the next points, but it's not as direct as with the ellipse. We're going to have to talk about that a little bit more. So let me draw this thing out a little bit bigger. And we'll take the one that faces left and right. We have our center here. We've already said that to get from the center to the vertex, that distance is given by A. And this would be the x squared positive. I should also point out too that A is not necessarily bigger than B like it was with the ellipse. The A is just attached to the positive part. So I guess that way we can think about it as being bigger, right? Because positive is always bigger than negative. But the A is attached to whatever the positive part is. We lead off with the positive. So this would mean that the A is attached to the x, meaning the x is the positive term here. The B is a little bit more complex. What that B is doing is it's giving us this length here, but there's obviously not a side there. So what that is setting up is an imaginary box. We go by A units left and right to get to the sides of those boxes. We go by B units up and down to get to the top and bottom of that box. And through the corners of those boxes are our asymptotes. So now I can draw this a little bit more accurately. Our ends, if we're to really extend them out, would have to be approaching those asymptotes. So hyperbola is, I think, definitely the most complex in terms of visualizing, because we have this idea of the imaginary box. That B is giving me my rise or my run to get to the asymptote. It's not really that there's an imaginary box there per se. It's easier to visualize by putting that in there. It helps us tie it back into the ellipse. The A is very visual. It's getting us to the vertices. The B is helping us figure out how much that rise or run is to get us to the asymptote. So we do need to write those asymptotes in there. They will be our controlling features. And if we think about the asymptote is a line. We know we can always find the equation of a line y minus y1 equals mx minus x1. Well, in both cases, x1, y1, both cases being opening up or down, x1, y1 is a point along that line, and we know the center is always going to be a point along that line. So we can write this as y minus k, and we'll figure out x minus h. That is going to be consistent. Now that slope is going to vary between the two, and that's going to be the difference. So if we think about the one that's opening left and right, that's the expanded picture I have here. The slope to get from our center to this next point, let's call it right here. We would be going up by B and over by A. And so our slope for this one would be B over A. But wait a minute, there's another asymptote, and that slope would be going down by B and over by A. So we actually have two different asymptotes with the same idea of the slope. It's just that we have two different signs. Not perpendicular lines. I will stress that they're not perpendicular. These two lines do not have to be perpendicular. They just have negative slopes. Remember, perpendicular, we'd also have to take the reciprocal. So we'd have y minus k equals b over a, x minus h. And we'd have y minus k negative b over a, x minus h. I have some students that ask, well, can I just write it as 1 plus or minus b over a? No, I do want you to write these out as two different equations, and the reason why is we are going to want to write those into slope-intercept form, so that way we can graph them easier. It's much easier to graph something in slope-intercept form. So these are just our initial line formats. We do want to solve those for y, and so because we're solving for y in both equations, I want to have both written out separately, because we're going to have two very different equations. The b's are going to be different. Let's do the asymptotes for the one that's going up and down. So we already said that the k and the h are going to be the same, but it's that slope that we're going to have to think about differently. So now if we think about the slope, the a we've already defined as the rise, the b would have to be the run. And so now our slope is going to be a over b. And we'll also have the negative a over b. Because we're still getting to those imaginary boxes, we're just doing so in a little bit different order. The a's are giving us our rise because the a's are attached to the y. The b is giving us the run because it's attached to the x. So those are going to be our asymptotes. And then the last thing I need to worry about still are the focal points. My tablet's running a second slow here. Give it a second to catch up. So our foci are going to be, we talked about this briefly with the ellipses, that the foci are somehow tied to the a squared and the b squared, and that is still true. But to find this foci, we're going to have to find this c. And c squared this time is going to be a squared plus b squared. And so we're going to have a different relationship for those foci. If we think about the foci for the one that opens left and right, the foci will be here and here. So we're changing the x-coordinate. So we'd have h plus minus c, comma k. And then for the one opening up and down, we're changing the y-coordinate, same way we did with the vertices. So we'd have h, comma k plus minus c. But again, those foci are occurring inside the curve. The foci are always inside the curve, meaning they're outside of the center. They're beyond where the vertices were from center. And so this is one of the most common mistakes I always see, because we have these two equations for C. This one looks identical to the Pythagorean theorem. The other one did not. It was completely opposite. We had that minus. The keys we want to be paying attention to when you're checking it, make sure they're inside the curves. That's the obvious, right? That's how we can obviously if they're right. And then the way you can kind of remember if you just need a trick, you're always using the opposite sign. So remember the ellipses is a plus in the standard form of the equation. We use the minus on the C. With the ellipses, we have the minus on the standard form of the equation, yet we're using the plus on the C. So those would be our foci. A couple last terms I want to throw at you. We have two other axes, kind of like we had a major and a minor axis. And let me just redraw this picture again, because I know there's a lot of information on it. With our ellipses, we had what we called the major axis, and that connected the vertices. With our hyperbolas, we are going to have a transverse axis, and so this is another way we can differentiate a hyperbola and an ellipse. Hyperbolas have transverse axes along with conjugate axes. We'll talk about those in just a second. Ellipses had major and minor. So transverse axis is equivalent kind of to that major axis. The transverse axis is a line segment connecting the vertices of the hyperbola. Obviously meaning it runs through center. Center being in the middle of everything, just like it was with the ellipse. The transverse axis is very intuitive, but because that other direction was less intuitive, we have to think about that imaginary box. Again, it is imaginary, but it gives us a nice frame of reference. And connecting the other sides of the imaginary box, so we have a line segment that doesn't really exist, but connects two sides that don't really exist. But to give us that measure, it is called the conjugate axis. The conjugate axis is a line segment connecting the sides of the imaginary box of the hyperbola that runs perpendicular to the transverse axis, and passes through center. Everything passes through center. So if we come back and think about the lengths of these things, again, kind of a weird idea. We have this imaginary box that just helps us get the ideas on paper, helps us figure out what's going on. We have these conjugate and transverse axis, again, just tying things together, helping us get ideas together. Conjugate axis kind of similar in theory to the minor axis. It is not necessarily the smallest though, because keep in mind the A is not necessarily smaller than the B, it's just the positive. And so it could be that these things are actually really close together. Let me draw another picture. Really close together, yet the imaginary box goes really far up. So it can be that the conjugate axis is actually bigger, unlike the minor axis, which is why we can't call it minor or major. But the major is like it, the transverse, in that it connects those vertices. So because the A is always referred to the positive, that will always be the transverse axis. Transverse axis has length 2A always, and the conjugate axis has length 2B. For the transverse axis, that would run horizontally in the case of the x squared being positive, vertically in the case of the y squared. So we do want to understand what these pieces are doing because they're pieces of information we might be asked for. They might also be given to us because if we have common names for things, even if it's kind of more abstract in terms of what they're actually measuring, if we have common names for things, then we can reference those elements, and they do have importance in the real world. Just because things aren't always visually obvious doesn't mean that they're not relevant. So, like we've done with ellipses, like we've done with parabolas, we're not going to worry about these formulas so much as we want to understand what the pieces are doing. So let's take an example. Let's say we have x minus 3 squared over 9 minus y plus 1 squared over 4 equals 1. Now I can tell this is a hyperbola. The first thing I always want to be thinking about is what shape do I have? I can tell this is a hyperbola because we have the x squared, y squared. We have the minus between them, and so that's a dead giveaway. If the signs are different, it is a hyperbola. On top of that, the coefficients are different, meaning it couldn't be a circle, but it couldn't be a circle right here because the sign was different, even if the coefficients were the same. So the first thing I'm going to do is sketch a picture. I have a positive x squared, which does mean it has to be opening left and right. I also know right away my vertex, that's always easy to see as long as it's in standard form, has to be 3, negative 1. Next, I'm going to start picking out my a, my b, and my c. Well, a is a positive, so it's going to be the square root of 9, which is 3. Same idea as the ellipse, we have to take the square root. The b is going to be the square root of that 4, has to be 2. So our c squared would be equal to 9 plus 4. Don't make that mistake that I just did. It does need to be the positive because we just talked about the fact that we are doing the opposite sign. So the c would be equal to the square root of 13. So now that we have all of those key facts, we can find all the other elements. We know the center is right here. To get to the vertices from there, we have to travel by a units. So I meant to call this my center, right? That's another mistake, moving too quick here. So our center is the easy thing to find. That's the 3, negative 1. The vertices are the elements that span left and right of that. So we're going to go 3 units to the right. That'd be 6, negative 1. 3 units to the left would be 0, negative 1. And it does not matter which one you put first. That is the same idea as with the ellipse. Next thing I'm going to do is get my focal points from my foci, just because I already have the C. So I would go from center to the right by the C, and then I'd go from center to the left by C. So 3 minus the square root of 13, negative 1. Next, we're going to work on the asymptotes, and these take the most work. So my asymptotes, we're going to sketch out that imaginary box. We have to move left and right by 3. Let me try and switch colors again. So I'd move left and right by 3. I'd have to move up and down by 2 because my b was 2. And that would give me that imaginary box in there. And so that's telling me my rise is 2 and my run is 3, or we could also have the negatives. Notice how I didn't reference the formula, I'm just thinking about what the picture tells me. So now my equations, y minus, well, the c value there, the center value is a negative 1, so we're going to have y plus 1 equals the slope of 2/3 x minus, our x coordinate of our center was 3, so we'll have x minus 3. That would be one of the equations. Our asymptotes always pass through center, so we can always use the center. Then the other equation has to have the negative 2/3 slope. I'm going to go ahead and put these into slope-intercept form just so they're easier to graph. So I've distributed. I'm going to subtract my 1 over. I do the same thing here. My distribute. That's going to turn into a plus. I'm going to subtract my 1 over. So notice not only are the slopes different, but my y-intercept's completely different as well, which is why I really encourage you to write out those two different equations right from the start. Figure out the two different slopes, write out those two different equations. And so just in the interest of time, I'm going to call those my asymptotes and not move them over to the right. But those are my asymptotes. And so now I have everything I need to graph this thing. So I'm going to start with my center, 1, 2, 3, negative 1. I know to get to my vertices, I have to go left and right by 3. 1, 2, 3. So that's going to be a vertex. Let me start labeling these things as well. It gets really messy if I don't label them. So my vertices, I have my center and the dead center. I have my imaginary box, or we can graph the asymptotes, it doesn't matter. But the imaginary box is telling me to go up and down by 2 units. So that would be the top, and then that would be the bottom. So there's my imaginary box. And through the corners of that box must pass my asymptotes. And notice how we passed right through center. So now I can go from my vertex and I can flare out to reach my asymptotes. My transverse axis would be double the A, and because my A was 3, my transverse axis length would be 6. That would be running horizontally. My conjugate axis length, that would be running vertically. That would be double my B, that would be 4. And so, just like I did with the parabolas, I started with a super inaccurate picture, a little diagram, and then finally, once I had all of my information, I made it more accurate. All right, let's look at one that is not in standard form. Standard form though, notice this is in general form, everything's been multiplied out, it's set equal to 0. And so if we want to figure out what this is, we need to put it into standard form. If we need to know its center, its vertex, all that key information, we need to put it into the standard form. So before we get started, it is a good idea to pay attention to what conic section you have. I don't want to go trying to get x's and y's on one side if it's actually a parabola. But notice I have that x squared, I have the y squared, and their signs are different, so clearly indicating to me that I do have a hyperbola and not one of the other conic sections. So first step is rearranging. The x's are already together, the y's are already together, but I do need to move the 10 over to the other side. Also, I need those coefficients on the x squared and y squared terms to be 1, so I'm going to factor those off. 3x squared, I had to factor the 3 out of the 12, that gives me a 4x. I'll go ahead and leave my blank so I can complete the square. I'm going to factor off that -2. I do need it to be a positive one, so that does mean I need to pull off the -2, not just the 2. If I divide the 8 by the -2, it's a -4. It's always one of the most common mistakes I see is forgetting to factor it out of both the terms. That means a negative as well. You got to change that 8 sign here because we had that negative we were factoring off. That's a little different than the ellipses and the parabolas. Now to complete the square, I'm going to have to add something here. I'm going to have to add something here, which means I need to balance it on the other side. So I'm going to have my pair of blanks there. So I need to figure out what to add here. I'm going to take half of this -4, that's -2, and I'm going to square it. But that's not just a 4. It's really a 4 times 3. Just like with the ellipses, I have to remember I have a coefficient now. That's 4 times 3, which is a 12. Then here I have half a -4. That is a -2 as well, and square it. But this isn't 12, right? This is 4 times a -2. And that's a -8. So we have to remember not only to figure out what this is, it's a 4, but it's not just a 4 because we have that coefficient, and we have to pay attention to the signs. That's probably the biggest mistake I see on these hyperbolas is forgetting multiplying really a negative here. So we have to subtract on the other side. We're not just always adding, strictly adding. Sometimes we might actually have a little subtraction over there. So now to finish up what this would look like, we have our x minus 2 squared, our y minus 2 squared, and then -10 plus 12 is 2, and then subtract 8 gives us a -6. I'm going to divide both sides by that -6, and so we get a x minus 2 squared over 3 goes into -6 -2 times, or 3 over 6 is 1/2. Then we have the y minus 2 squared. We had a -2 over -6. That's going to give us a 3, or 1/3. 2 over 6 is 1/3. So we have the y minus 2 over 3. So notice what's actually happened. It looked like at the first, the x squared was positive. It was positive, right? That would make us think that this hyperbola is probably going to open left and right. But when we had to divide out that negative number, that switched it. So we can't necessarily tell, really we shouldn't even try to tell at the start, whether it's going to open left, right, up, down, whether what the center is, what the vertices are. I'm just pulling that negative to the front so I can see that clear structure of the y's minus the x's. The only thing I can tell from the start, from that initial equation, is if this thing is going to be an ellipse, a parabola, a hyperbola, or a circle. That's all I know. Everything else I have to determine after I complete the square. So now I have a form, the standard form, that I can work with. I do know now that this thing is going to open up and down, so I'm just going to get my little sketch to remind myself. And that is because the y's are positive. The center would be the point 2, 2. We switch both of those signs and they both become 2. The a is going to be the square root of 3. The b is going to be the square root of 2. And so our vertices, if we look at our picture, this is why our picture is helpful. Our vertices from the center would be going up and down. I got those wrong. Let's try that one more time. They would be up and down right here and right here. And we have to travel by that a to get there. So our vertices would be 2 plus the square root of 3. I did that completely wrong. We just said we have to go up and down. X is going to stay the same. We're going up on the y, so 2 plus the square root of 3 on the y position, and 2 minus the square root of 3, because again we are going up and down, the x is not changed. The foci, I need to find the c. Well, c squared would be equal to the a squared plus the b squared, and so our c will be equal to the square root of 5. And so our foci would be 2 plus the square root of 5, and 2 minus the square root of 5. Notice we're doing those to the y's once again. I need to figure out the asymptotes, so let's think about those next. Let me scroll over here. If we think about that imaginary box, we know that the a, this distance here, is the square root of 3. The over is the square root of 2. So our rise is the square root of 3. Our run is the square root of 2. And so that will be our slope. We could write it all under one square root. Again, I don't care that you're rationalizing. And then we would also have the negative slope for the other asymptote. And so if we write down what those asymptotes are, we would have y minus, well, remember what our center was, is 2, 2. Y minus 2 equals square root of 3 over 2 x minus 2. And then the other one would be y minus 2 equals the negative square root of 3 over 2 x minus 2. And so we'd have y minus 2 equals the square root of 3 over 2 x minus 2 square root of 3 over 2. If we were to rationalize, that would clean up a little bit, but it's not going to be a ton because they're never going to be like terms. So we get y is equal to square root of 3 over 2 x minus 2 square root of 3 over 2 minus 2. Let me just show you what it would look like rationalized real quick. So we'd have the square root of 6 over 2x minus the square root of 6, because we would multiply by the 2's on top and bottom. The 2's would cancel. Radical 2 on top and bottom. Minus 2. So notice they don't clean up. Even if we rationalize, we still can't combine them. They are not like terms, so either of those is fine. And then here we'd have y minus 2 equals the negative square root of 3 over 2x plus the square root of 3 over 2 times 2. I forgot my 2 there. And then adding that 2 over, we'd have y equals the negative square root of 3 over 2x plus 2 square root of 3 over 2 plus the 2. And so those would be our asymptotes. Then finally, to graph this thing out, I'm going to start with my center of 2, 2. I'm going to use that a and the b to create my imaginary box. Well, here we're going to have to do a little bit of rounding again, but we can see that the square root of 3 and the square root of 2 both very close to one another, so it's going to look pretty even both ways, but let's see. So the square root of 3 is 1.73, so we're going to have to, remember that's the a, so that's how much we're going up and down. So just under 2, or 1 3/4. That would be a vertex. This is our center. And then down by that 1.7, and that would be another vertex. The other sides of our imaginary box, we would need to go over left and right by 1.4, so just under 1.5. So about there and about there. And that would give me my imaginary box. And that marks a little bit over too far because it should be balanced, so it should be about there. And so then I'm going to draw my asymptotes to the corners of those imaginary boxes. Again, graph paper makes this a little bit easier. And I want to draw my curve going through my vertex, approaching my asymptotes. So there would be my hyperbola. And just like we've done on the other conic sections, we should be able to take information and find the equation. So write the equation of the conic section with vertices of -3, 2 and 3, 5 if the slope of the asymptote is the slope of one of the asymptotes is 1/3. And let's see how we're going to do this. First thing I'm going to do is sketch it out. The same way we've done everything else. Negative, and I meant for that to be negative. They both need to be negative, otherwise this is going to be a little impossible. So -3, 2 is our first vertex, and then -3, 5, again, that's that point that I switched. 2, 3, 4, 5. That's our other vertex. And so we know that those vertices have to point away from each other, so this would have to be the general shape of it. We can see that it's opening up and down. And I should always ask myself the question, what shape do I have, right? I kind of jump right into that. Because we are concentrating on hyperbolas right now, I kind of knew it was going to be one. But we should always ask ourselves what shape we have, because what happens when I scramble all these conic sections together? Like we talked about up here, right? We saw that we had the negative, so we knew it was going to be a hyperbola. Here the key is we have an asymptote, right? That's the only conic section that has an asymptote. So we want to be looking out for those key differences between the conic sections. And in the next video, I said I was going to create one more that showed the differences in the conic sections that helped us figure out which one is which. Kind of talks about that, but we want to think about the key characteristics that each one has. Asymptotes only belong to the hyperbolas. The minor major axes only apply to the ellipses. The transverse conjugate axes only apply to hyperbolas. The p-value, or the single focal point, that's only true of parabolas. Circles only have a radius, so there are key differences, right? So now that I know it opens up and down, I'm going to write down the general format. Y minus k squared over a squared minus x minus h squared over b squared equals 1. And so what I'm looking to find is the hk, the center, and then the a and the b. So there's a few things that we can figure out pretty quickly. One is the center. The center has to occur exactly halfway between the vertices. We've seen this before. We can see that the x value is constant. The -3 is constant. We need to be halfway between 2 and 5. Well, halfway between 2 and 5, it's 3 units between them. Half of that is 1.5, or you could add the 2 and the 5 and then divide by 2. We get 7/2, right? So kind of two ways of doing that. Add the 2 and the 5, divide by 2, or figure out how much space is between them, 3 units, and then take half of that. So there's our center. So already we can write y minus 7/2 squared minus x plus 3 squared, and we need the a and the b still though. Okay, so let's move on to the next bit of information that we're given. We can still use that a little bit more actually. The vertices tell me a little bit beyond just the center. They also help me figure out that a value. So let me clean this up for just a second. My eraser is not working. So just make that a bigger point. That's my center. This is my vertex. So this little distance in here, there it goes. That is my A. So I need to figure out how far it is from center to one of the vertices. from 7/2 to 5, that is 3/2 of a unit. Or the other way we could figure that out is we need there's 3 units between 2 and 5. Half of that would be the A, so 3/2 will be my A. Now I need to figure out still my B. I can go ahead and plug that A squared in there, but I'll wait till I get my B. The last thing that I'm told is that the asymptote has a slope of 1/3. That would mean if it goes up 1, it goes over by 3. And so just kind of a ballpark, that'd be kind of what it looks like. But if we think about what the slope of this is in relation to the A and the B, well, we went up by A, and that means obviously we'd have to go over by B, and we must be dealing with the positive asymptote here, otherwise we'd just make it a negative. So the slope is equal to A over B. They've told us the slope is equal to 1/3. We just found our A to be 3/2. So I have a nice little equation here that I can solve for B. If I want to solve for B, I'm going to have to multiply that B over to the other side. And then I would have to multiply by 3 on both sides. And so we get our B to be 9/2. That would make the B all by itself. We get B to be 9/2. And so now we have our A, we have our B. We just have to remember that when we're putting them in our equation, we have to square them. The A goes under the Y because the A is the positive element, it's opening up and down. 3/2 squared is 9/4. And then the B was the 9/2. 9 squared is 81. 2 squared is 4. So we get 81/4. And that would be our equation. And just like we discussed with the ellipses, I do not care that you make these fractions nice and pretty. You don't need to move the 4's up. We can leave the fractions in fractions because our goal is the standard form of the equation. The standard form has it over A, has it over B, and so that's it, we're done. So again, the key to any of these problems is we want to know what the key elements represent. What does the A do for our problem? What does the B do? And it depends on the type of conic section we have. What does the P do in the case of the parabola? So if we understand the pieces, we don't need to memorize just the formulas that I wrote up there at first, right? We kind of drive those by knowing what the pieces meant. So I would recommend do not concentrate on just memorizing the equations. Don't memorize the formulas. Learn what the pieces do. And if you can understand what those pieces do, we've seen similarities between all 4 conic sections now, so we can understand how they all behave. We've got to recognize first off what conic section it is. Then I would recommend sketching a picture and then think about what are the key properties of this conic section. Write those elements down, figure out what those elements represent.